Hi there, in this video I'm going to discuss the interpretation of the energy diagrams. In an energy diagram you will find the free energy, then the reaction coordinate. The free energy we can be able to get it using the calculation. Delta G is given by enthalpy change plus temperature times the change in entropy. So by looking at the reactants and products, we can be able to quantify the change in delta G. So like in this case, the products seem to be of lower energy. So when the products are of lower energy than the reactants, then we can say that the reaction is hexagonic. An hexagonic reaction is spontaneous. It favors the forward reaction because the products are going to be stable. They are of lower energy. Now, by looking at that, we can consider the processes that take place in between. Like in this case, which position in the energy diagram represents a transition state. Now, a transition state always occurs at the peak, that is at the energy maximum at this point here. So the transition state usually only exists for a fleeting moment. We can neither isolate them nor observe them, but we can be able to predict the structure based on an understanding so that we can figure out how it's going to generate the product. Okay? Which position in the energy diagram represents an intermediate? Now the intermediate is found at the energy minimum, so at that position. So in this case we have two transition states, then there's an intermediate. Intermediates usually consist long enough to be observed, so we can isolate and even analyze them. So in this case, again, let us see what happens. We have reactants and products. The product seems to be stable, so this reaction favors the formation of the product, but it also generates an intermediate, which then is going to reorganize itself to give us the product. So you need to be able to determine the position of the intermediate, the position of the transition state. You need to determine the reactants and the products and which ones are going to be stable, and even be able to predict the spontaneity of a reaction. So we said that the transition states only exist for a very short time, and that we cannot be able to isolate them. So how can we predict the structure of the transition state based on an understanding? Well, this theory was developed by George Hammond, who was actually a chemistry professor at Iowa State University. Now, let us look at the Hammond postulate and how it helps us to predict the structure of the transition state. So here we have the methyl bromide reacting with the chloride. And what happens is this reaction takes place in one step because we do not have an intermediate, but we have a transition state. And we actually have different transition states. We could have another position there, another one there. So they all occur at the closer to the maximum. But we can be able to predict the structure as we move to the formation of the product. It means the product is going to be forming as we move down until we end up with the product that we are looking for. So at each of these positions, we can predict the structure of the transition state. So according to Hammond postulate, he came up with a theory that the 2 points continuous on the reaction coordinate that are close in energy should be similar in structure. So as we move, let's say like at this position, what is happening is the methyl bromide is trying to attach itself to chlorine. So it's getting closer to chlorine, but it is still attached to bromine. So chlorine is moving closer, but it's still not close enough. So as chlorine comes in, the bromine is kicked out. So chlorine gets closer, bromine moves away until it reaches a point where now the chlorine is the one that is attached and the bromine is completely kicked out. So at every given point, we can be able to predict the transition state so that at the end, we are going to have chlorine attached and then bromine being completely removed from the methyl bromide that it was close to. So that is according to the Hammond postulate. For practice purposes, let us look at the kinetics versus the thermodynamics of the reaction. So in each case, identify the product as being thermodynamically or kinetically favored. Now in part A, if you look at the starting materials, these starting materials could either form E and F, or they could form C and D. So between E and F and C and D, we want to find out which one is going to be kinetically favored and which one is going to be thermodynamically favored. Thermodynamic factors are those that help us to predict the stability of the product. So there are these 4 that I already gave you guys in the notes. So in order to find out if the formation of the product is thermodynamically favored, we look at the energy, the delta G. If it has the lowest delta G, we are going to say it is the thermodynamic product. Lowest delta G, thermodynamic product, okay? Kinetic factors include the activation energy, things like a catalyst, temperature, concentration of reactants. So in other words, we are going to be looking at the either the intermediate, or we're going to be looking at the transition state, or things that affect the stability of the intermediate, okay, not the product. Thermodynamic factors are to do with the product. Kinetic factors are to do with the reaction rate, steric effects, and things like that. So here we are going to look at the activation energy. So for the one in blue, in green, sorry, we're going to look at the activation energy, which is going to be that. For the one in red, we are going to look at the activation energy, which is going to be like that, EA. So the one in red has a lower activation energy. Lower activation energy, it implies that the barrier to be overcome in order for the reactants to collide is not that much. So this reaction is kinetically favored. Formation of E and F is favored kinetically, but the product is not stable. So we say that this is going to be a kinetic product because it is favored by a lower activation energy. It's favored by the kinetic factors. While the other one, the thermodynamic product, is not favored by the kinetic factors, but only by the thermodynamic factors. Let us go to part B, where we have A plus B to give us E plus F, and then C plus D. Let's find out which one is thermodynamically favored and which one is kinetically favored. So by looking at the product, C and D is of the lowest energy, so that's going to be the thermodynamic product. Then let us look at the activation energy for each of them. And when we do that, we realize that the activation energy for formation of C and D, the activation energy is lower, which means it is kinetically favored. So formation of C and D is both kinetically and thermodynamically favored. The formation of E and F is not thermodynamically favored because it's of higher energy. The product is not of lower energy compared to C and D. And then the activation energy is also higher, so it's not even kinetically favored. So then formation of E and F is not favored by any of those factors. So we are likely going to have C and D being formed in large quantity. It's the one that is favored.